Hello, everyone. It is my great pleasure to introduce Luca De Feo, a true pirate who masters the dark arts of isogenies. These are a highly valuable treasure that promise safety in the fantastic but dangerous land of quantum computers. But make no mistake, Luca is no ordinary pirate. He's already conquered the first milestones with SIDH and Psych, and is uncovering new hints in this quest with C sign, ski sign, and on the C side. So today, he's going to tell us what's next in his search for the great isogeny treasure in isogeny land. All yours, Luca.
Thank you very much for the introduction, Patrick. It's very cool. I wasn't expecting this. I hope to be up to the promise. And I already see I cannot write correctly the date of today, but never mind. So, as the title says, my goal here today is to try and predict the future. So something more as a magician than a pirate this time. And so I didn't bring my pirate hat. Sorry to disappoint you. But of course, before going to the future, we need to start from the past, right? So we need to look at the history of isogeny-based cryptography. And I will start from the very beginning, from the singularity, the point in time which we can't even observe, which is 1997, when the very first isogeny-based scheme was presented. It wasn't presented in a paper, it was presented at a seminar in Paris. And it was Jean-Marc Couvaigne who gave this talk entitled "The Hard Homogeneous Spaces," which was a very cute idea, but which wasn't accepted for publication at Crypto 97, and so stayed in a drawer for about 10 years. And so after this Big Bang, the initial formation of the isogeny universe, we went through a kind of dark age where just no one was speaking about isogeny-based cryptography. There were just a few people who heard Jean-Marc talk, the reviewers of Jean-Marc's paper, and that's pretty much it. And so isogeny stayed quite silent for a while. And it's only like 10 years later when things started to get moving, and we started to have a phase which is similar to the star formation phase in our universe, when you start to see the first isogeny-based protocols aggregate and take shape. So things really got started in 2006. That's when Charles Goren and Lauder published their hash function paper. And that's also the year where Rostov-Sem and Stolbunov published the key exchange idea, which turned out to be exactly the same idea that Couvaigne had presented 10 years before. But they came independently to the same discoverer. And this idea was presented in Paris again at École Polytechnique this time in 2006. And that's more or less, I think, when people spoke to Couvaigne. And so this old idea was resurrected and appeared on the print finally. So that nowadays this basic scheme is attributed to Couvaigne, Rostov-Sem, and Stolbunov. And it is the very first key exchange scheme based on isogeny. And it's also thanks to Rostov-Sem and Stolbunov that we started talking about isogenies as a potential post-quantum candidate. Things stayed quiet for a while. Isogenies go in bursts, a little bit like this. So not much happened in the years between 2007 and 2010. At least not on the side of isogeny-based cryptography. Of course, there were lots of work on isogenies. That's when I did my PhD, and I was indeed working on isogenies. But isogeny-based cryptography was still these crazy ideas which no one really believed in, which maybe one day. And then in 2011, something happened, something notable happened. David Zhao and myself, I was visiting David Zhao as a postdoc in the University of Waterloo, and he presented to me his beautiful intuition about finding a common group, like a middle point, and in some of a meeting point between the Charles Goren and Lauder hash function idea and the key exchange by Rostov and Stolbunov. And this is what ended up being SIDH that you know today. And so SIDH, of course, is notable because it was the first isogeny-based scheme, which was the first post-quantum isogeny-based scheme, which was practical. You can say that Charles Gore and Lauder hash function was practical, but that didn't, of course, have any kind of post-quantum application in mind. And it's not extremely practical if you compare to other hash functions. Things stayed quiet again for like 4 or 5 years. Not much happened between 2011 and 2016. A couple of ideas built on top of SIDH were published by Zhao and his students. But things really took an upward turn in 2016 when we reached this inflection point. So in the history of the universe, the inflection point is this point where dark energy dominates matter. And here we start having dark isogenies dominating, I have no idea what. And this, of course, was spearheaded by NIST announcement of a post-quantum competition. So, of course, suddenly people start getting interested, and then you have a boom, a huge explosion in the number of new isogeny schemes. An important turning point was 2018 when Kastrick, Lange, Martindale, Pani, and Wren presented Seaside. So be careful, SIDH, you just pronounce SIDH, but when you add the C, it becomes Seaside just because reasons. Because isogenistas like to make puns, essentially. And so this was a very important step for isogeny-based cryptography because it gave a new building block to build a lot of advanced schemes, which was very flexible, much more flexible than anything we had before. And was also efficient, which was something really new if you compare with Kuveni, Rostov, Stolbunov idea. And so starting from that, we get CFISH, which is a pretty good isogeny-based post-quantum signature, which is even more interesting if you look at advanced schemes like threshold signatures, ring signatures. And then recently we got something even more surprising in the way of isogeny-based signatures, which have been a challenge for a while, but finally last year we were able to introduce a ski sign, which is the most compact post-quantum signature to date if you measure the public key and signature size combined. So these are the schemes that the names that are going to come mostly in my talks: SIDH, Seaside, CFISH, and ski sign. Because these are probably the ones that really do have a practical impact. You can expect to see used in practice someday. But of course, there's much more than this, and I will try and reference them. Okay, now, where did isogenies come from? Because, of course, this is the history of isogeny-based crypto, but isogenies were not invented for crypto, of course. They had been existed for centuries. The name itself, isogenies, was invented by André Weil. In his Foundations of Algebraic Geometry, he needed a name to distinguish isogenies from other kinds of morphisms. Up to André Weil, everything was called an isomorphism, but he found that the name wasn't convenient. It really needed a special name for this. And he found this cute name, which really sounds a bit mysterious and really sets apart isogenies from anything else. And so, of course, isogenies have been a central tool in algebraic geometry for more than 1 century. But they came really to cryptography only in the 80s, 90s, when we started working with elliptic curves. And so we discovered the elliptic point counting algorithm by Skov, and then the improvements by Elkis and Atkin. And so it's these improvements, especially in particular the Elkis improvements, that really gave a motivation for cryptographers to do isogeny computations. This is really the beginning of, as Elkis used to call them, effective isogenies. So really the theory of algorithms to compute and evaluate isogenies. And so this is the way that isogenies came into cryptography. And then a couple of years later, when isogenies were really a fundamental tool in the algorithmic theory of elliptic curve cryptography, people started wanting to use them to do discrete logarithm reductions between discrete logarithms of elliptic curves. And so this is another important turning point, because this is really what motivates the move from looking at an elliptic curve and looking at isogenies of this elliptic curve, which is the way you do point counting, and moving to a different point of view, which is that of isogeny graphs, where you just globally look at all elliptic curves and isogenies between them. So this is how really isogenies came into the game, and this is what really brought isogeny-based cryptography in a sense. So just to give some intuition and to explain what an isogeny is, if you never heard about them, you already probably have an idea, if you know about elliptic curves, of scalar multiplication. Scalar multiplication is just taking a point P on the elliptic curve. You know that elliptic curve has a group law, so you can add points together, and so you can also multiply them by a scalar. So scalar multiplication is taking a point P and adding it to itself n times. And so a scalar multiplication is an endomorphism of the elliptic curve because it's a map from E to itself. It is a group morphism, of course, it respects the group structure. It has a finite kernel, this is very important. It is surjective if you look at the algebraic closure. And most importantly, it is given by rational maps, which means that you really have explicit formulas to compute this scalar multiplication. Now, what's an isogeny? An isogeny is a generalization of scalar multiplication, where you just think of a map phi, so your isogeny is phi, which maps points to points, but is not going to map points of the elliptic curve to itself. It's going to map points from some elliptic curve to a new elliptic curve, E prime. It is still going to be a group morphism. It is still going to have finite kernel, but now you just allow yourself to take any finite subgroup of the elliptic curve as kernel. And so this is just what an isogeny is, really, with minor details added, like I'm really talking about what is called separable isogenies by number theorists, but this is really an isogeny. Choose a finite kernel. This is going to be the kernel of your map, which is going to map to a new elliptic curve. They're still going to be surjective, and they're still going to be given by rational maps. They're just going to be given by rational maps of a degree which is equal to the size of the kernel. And this degree is a very important invariant for an isogeny, which more or less measures the complexity of computing this isogeny, how much information is encoded in the isogeny, how difficult it is to compute this isogeny. So just to show you a very simple example, let's take finite field F11. Here you have two elliptic curves, and in the bottom corner you see an isogeny between these two elliptic curves. So trust me, this is an isogeny. The arrows show how points on the left are mapped to points on the right, and the point in red is the generator of the kernel. This is a point that goes to 0, and so 0 is represented as a point at infinity in my picture, so it's outside of the slide. And another important fact you can see in this figure is that this is a degree 2 map. You see it in the degree here, which is a square. You see it because 2 points, like it is a 2-to-1 map. You can see like 2 points going to a single point, if I circled it correctly. I didn't. Anyway, like if you look at the picture, you will see that each point has 2 preimages, which is very similar to the square root map on a finite field. So in a sense, isogenies are also generalization of the nth root map of finite fields. And so this now lets us understand what I meant when I was saying that people used isogenies to reduce the discrete logarithm problem from one curve to another. So a very important theorem, the Serre-Tate theorem, tells that two elliptic curves over a finite field are isogenous if and only if they have the same number of points over that finite field. So if I give you two elliptic curves which have the same order, and this is something that you can test easily by counting points, then you know that there's going to be an isogeny. Doesn't mean it's easy to find this isogeny. Actually, this is the whole point of isogeny-based cryptography. But if you can compute that isogeny, that is a group morphism, and so that can be used to transfer the discrete logarithm problem from one curve to the other. And so this is what went behind the ideas in the early 2000s, like the Galbraith-Hessen-Smart attack, which was also developed by Menezes and Teske. So suppose that you have some weak curve, E, and then you know it's weak. You have a good attack on the discrete logarithm on this curve, and you know, of course, its number of points. But you are given a curve E prime, which has the same number of points as E, but on which you don't know how to break discrete logarithm. If you can find an isogeny from E to E prime, it's the same. From E prime to E or from E to E prime, it's going to be equivalent in the end. Then you can transfer the discrete logarithm problem from the supposedly strong curve to the weak curve. And the idea at the time was that doing this isogeny search in some circumstances may be more efficient than directly attacking the discrete logarithm on E prime. So for example, in a generic way for ordinary curves, this would give a fourth root attack instead of the square root attack you get from polar law. And in some specific circumstances, you can even hope that you have an even better attack. This is not the only way to use this idea. Zhao, Miller, and Venkatesan used this idea to show that there is a sort of random self-reducibility of discrete logarithms among curves in the same isogeny class. So a kind of a reduction to the average case, similar to what we have for lattices. This is what gave birth to the concept of isogeny graphs. Because when you think about isogenies, you really want to ignore isogenies of degree 1, which are isomorphisms, which just preserve the elliptic curve structure more precisely. So what you have seen in this animation is an elliptic curve that gets slanted and then a little bit moved. All these linear transformations will essentially preserve the same algebraic structure for the elliptic curve. And all elliptic curves that are the same up to a linear transformation will be classified by an invariant, which is called the J invariant of the elliptic curve. And so here you see the formula. It's something that's very easy to calculate. So it's very easy to test whether two elliptic curves have the same J invariant. And it's also very easy to find the isomorphism between two isomorphic elliptic curves. So all the problems are very easy to state just up to isomorphism. And also scaling is an isomorphism. So we really want to zoom out completely and just look, instead of looking at elliptic curves, look at them as isomorphism classes. Look at them as J invariants. And then we're just going to think, are these two isomorphism classes of elliptic curve connected by some isogeny? And of course, isogenies are also going to be up to isomorphism. And so this is really the beginning of the concept of an isogeny graph. Next step is that you just forget about the direction of the arrows, because you know that you have a very important theorem that tells you that whenever you have an isogeny from some curve to some other elliptic curve, then you have something that's called the dual isogeny that has the same degree and goes back in the direction. So you really can just ignore the direction and draw undirected graphs. And this is something that actually was initiated much before isogeny-based cryptography. Really, the origins of this idea is in Mestre, La Méthode de Graph, which dates back to the 80s. And then the theory of isogeny graphs was very much developed in Coel's PhD thesis, where he generalized Mestre's idea to give an algorithm to compute endomorphism rings of supersingular curves, which still today is the best algorithm we know to solve this kind of problem. And then in the next years, people started working on this theory of isogeny graphs more in detail to try and solve all these problems in cryptography. This is, for example, where the name Nisogenin Volcanos was created by Fouquet and Morin. And so the idea of an isogeny graph, like the one you see in the picture in the slide, is that your vertices are elliptic curves up to isomorphism, and your edges are elliptic curves up to isomorphism. And then, depending on which restrictions you make on the vertices and the elliptic curve, on the elliptic curves and on the isogenies, you can have many different shapes and kinds of graphs with many different properties. So what you are seeing in this picture is what is called a Nisogenin volcano. But other things you can have are going to come in one slide. So before I'm going to show you the isogeny graphs we use in cryptography, I just want to make an observation, which won't surprise you probably, but is the fact that, of course, cryptanalysis follows cryptography. Like you propose cryptosystems and then you try to break them. But there is also another direction that flows from cryptanalysis to cryptography. And this is a way that progress in cryptanalysis gives new ideas, which eventually may lead to cryptographic progress to creating new cryptosystems. So this has happened repeatedly in the history of cryptography. So just to stay in the elliptic curve word, think about the MOV attack on supersingular curves, on the discrete logarithm in supersingular curves using pairings. 7 years later, you have the birth of pairing-based crypto with Drew tripartite Diffie-Hellman-Key agreement and Boney and Franklin IB scheme, which of course was the beginning of a huge amount of research on pairing-based cryptography. And then history repeated itself with the isogeny graphs developed by Galbraith, Hess, and Smart, and all the people around who were looking at how you reduce these discrete logarithm problems. And then 7 years later, you get these ideas by Charles Gordon and Lauter, Rostov and Stolbunov on how to use isogeny graphs to make new cryptography. So to be fair, isogeny-based cryptography was invented in 1997 by Couvain, but Couvain didn't have this point of view of isogeny graphs. So this is really something that helped accelerate, I think, discovery in isogeny-based crypto. And so this is something that we see happening often in history. And so here are your isogeny graphs that we like to use in isogeny-based crypto. So you see you have two very different kinds of structures. One that looks very regular on the left, which is what some authors, including me, like to call complex multiplication graphs, because really their structure is governed by the theory of complex multiplication. And this is what's behind the Couvain, Rostov, and Stolbunov key exchange, behind C-side, behind C-fish, and yet a lot of other schemes in that family. On the right, you have what is called the full supersingular graph, which, as you can see, it looks much less structured. There is certainly much less symmetry in this graph. And this is the graph that's behind SIDH, SkiSign, and many other schemes that work with supersingular curves over the algebraic closure. So the full set of supersingular J invariants. And so whatever isogeny graph you choose, your fundamental problem will be something, your fundamental hard problem will be something that is called the isogeny path problem, which is the problem of given two elliptic curves, like the blue dots in this drawing, find a path between them. This will not always be your effective hardness assumption. This will really depend on the scheme. Some schemes will depend on the isogeny path problem in general. Some schemes will depend on looking for loops in the graph, like the one you just saw before. Some other schemes will depend on having some path between two elliptic curves, find an alternate path between the same elliptic curves, like the one you're seeing now developing in real time under your eyes. So all these kind of isogeny problems will give rise to different hardness assumptions that will be used differently in schemes. And so you have this mother of all problems, this generic isogeny problem, which is really the most generic and the possibly most secure problem, the one which if you can break, then you can break everything. That's up there. But then in practice, different schemes will depend in different ways on this problem. So for example, C-side and C-fish will depend on the generic isogeny problem, but restricted to the class of supersingular curves over FP. SIDH and Psych will depend on the isogeny path problem, but where you know that the path is unusually short in the graph. Still large enough that it's hard to find, but unusually short, etc., etc. There will be lots of variations to this problem. One thing you can see is that obviously the difficulty of solving the isogeny path problem is going to give you a one-way function. We know how to evaluate isogenies efficiently, so we can construct isogeny path. But then if you're asked to recover the path only given to two extremal points, that's a hard problem. So you have a one-way function, but of course a one-way function is not a lot. You really need more structure to do some interesting cryptography, at least some interesting public key cryptography. And so this additional structure is going to come from various theories. The most important one is certainly complex multiplication, which is a very venerable theory, which is more than 1 century old, and which makes a link between three different theories. On one side, you have class field theory. On the other side, you have elliptic curves. And on the third side, you have modular functions. So this is a very beautiful theory that links all these topics in a very beautiful way. In isogeny-based crypto, we usually ignore the modular functions part. Of course, it plays a role. It's useful, for example, to compute modular polynomials. But we really focus on class field theory and analytic curves. And here you really have these important correspondence between abelian extensions of number fields. So number fields to which you adjoin the square root of a negative number, and analytic curves which have endomorphism ring isomorphic to an order in this same quadratic imaginary number field. So, of course, this is a bit complicated if you are not used to number theory, but there's a lot of objects to introduce to understand this theory. But just to give you an important element of intuition, what counts here is the Galois group of this abelian extension of number fields, which is going to be represented effectively by something that is called the ideal class group. And this is something that we know how to represent. We have been using in cryptography for a while because it's a very computational object with which you can really even try and do crypto. And it's, for example, one of the most used implementation objects to instantiate groups of unknown order, which of course are important in many applications in cryptography. And so on the other side, what you have is the set of all analytic curves with what we say complex multiplication by this square root of minus d. So these are analytic curves whose endomorphism ring is isomorphic to, all these endomorphism rings are isomorphic to the same quadratic imaginary order. And so the fundamental theorem of complex multiplication tells you that there is a group action of the class group, so of this Galois group, which is represented by the class group, on these sets of analytic curves. And now we can just get back to something more concrete, maybe more manageable for cryptography, which is this concept of group action, which is a very mild generalization of a group. Instead of just having a group, in a group action, you have a group and a set. So the group, I'm going to call it G, and the set I'm going to call E. And then you have an operation, which is you combine an element of the group with an element of the set, and this produces a new element in the set. So this operation, I'm going to denote it by star. So G applied to E is going to produce a new element E prime. And so if you want to think about the group action, which you definitely know and which you've already seen, you can think of exponentiation. So this is strange because here you have a group that acts on another group. But so you can think of the exponents of a cyclic group to be acting on the elements of the group. So when you apply A to some element G, what you get is G to the power A. So this is a group action. And so what essentially makes a group action is a compatibility condition, the fact that when you act by different elements, so when you act with G and then you act with G prime, first G and then G prime, what you get is the same thing as you act by the product of G and G prime. So this is the fundamental compatibility condition you expect from a group action. And of course, you want the identity to act in a trivial way. So just to not do anything by action. And when we do cryptography, we really restrict to finite abelian regular group actions, where the group is finite and abelian, and where for every pair of elements in the set, there is one and only one element of the group that sends one to the other. So this is what we call a regular group action. And so, like, you can really, it's an easy exercise to make a regular group action from a cyclic group, for example, by having the exponents act on the elements of prime order in the cyclic group. And so if you add some cryptographic concept to this group action, you really get to the original idea by Quaternion, the one that he called hard homogeneous spaces, and which is probably easier to better called just cryptographic group action. This is probably a more intuitive name, which is the idea of having a group action which is combined with a one-way function. So evaluating the group action, it's the one-way function. So evaluating it, it's easy. You have algorithms to do it. But inverting the action, so given two elements, finding the group element that links them, it's a hard problem. And so this is really the theory that's behind the Couvin, Rostov, and Stolbunovsky exchange, behind CSI, behind Cefish. and which gives rise to many different schemes, advanced schemes, like threshold and ring signatures, hash-proof systems, oblivious transfer, verifiable random functions. So there's a huge amount of primitives which you can realize from this framework of cryptographic group actions. And if your cryptographic group action happens to be quantum safe, like it's the case for Seaside, then you even have quantum safe instantiations of these schemes. Which is why, in the end, Seaside happened to be so popular, and there was so much following on Seaside, because essentially it's a very easy tool to manipulate, which you don't really need to understand the number theory, the class group action, the isogeny stuff. You just need to understand what a group action is, and then you can just make new protocols. So this is a very powerful tool, which should be in the toolbox of any theoretical cryptographer, in mine and also other cryptographers' opinion. But then, of course, this is just part of the picture, because this does only cover the part of isogeny-based crypto which is related to Seaside and Quaternion-Rostov and Stomp-Lobunov. If you want to talk about SIDH and other schemes, then you need to go to something that's way more complicated and unfortunately much less easy to present to a general audience who has no familiarity with number theory. And so here I'm just going to to make a huge leap of faith and just ask you to believe what I say. So you can generalize this idea of complex multiplication having these group actions to more general, larger classes of isogenies, of isogenous elliptic curves. So all you want to have in the end is something that's called an orientation, a quadratic orientation, a concept that was essentially implicit in Seaside and related ideas, but which was really put on paper by Colo and Coel. And which is the idea that you want to identify some subring, some quadratic imaginary order, which sits inside the endomorphism ring of your elliptic curve, and at the same time sits inside some quadratic imaginary number field. Now, if you think about the Quaternion-Rostov and Stomp-Lobunov scheme, this inclusion will be just equality. So the sitting inside is really trivial. You will just have an equivalence, which will be just determined up to complex conjugation. So this is really the simplest case you can imagine, but you can go more generally, look for supersingular elliptic curves where the endomorphism ring is not going to be isomorphic to an order in a quadratic imaginary field. It's going to be a much higher dimensional object. Instead of being a two-dimensional object, it's going to be an object with 4 dimensions, which we call a maximal order in a quaternion algebra. Now, this sounds very scary, and I'm not going to torture you with what a quaternion algebra is. But the interesting thing is that, okay, it's complicated. It's not even a commutative ring, so it's non-abelian. It's very messy when you try and do things with it. But at least it's an algebra, so it has algebraic structure, and you can do lots of smart things with it. And now the interesting thing is that when you look at this larger endomorphism ring, there's infinitely many ways to put orientations inside this ring. And so you have a more general theory of complex multiplication, which some people call quaternionic multiplication, some other people call just the Doring correspondence, and which tells you how these complex objects, these quaternion algebras, act on the set of supersingular curves. And this action is not going to be a group action anymore. You're going to have something that looks kind of like this picture, where you have the full graph of supersingular curves, and then you see all these circles that are being drawn on the graph. These are orbits of class group actions. So you have many class groups separately acting on some subgraphs of the full isogeny graph. And so, of course, you can just restrict. So each of these cycles is representing one possible orientation of some subgraph of the supersingular graph. But then the nasty thing is that you can interact. You can make linear combination of these different interactions. And so what you get is a huge mess of lots of different class groups acting on the same supersingular set and making things very hard to follow because everything does not commute. So this means that it's much more difficult to make a key exchange scheme, for example, and yet it is still possible, and this is what SIDH does. So this whole story of the Doring correspondence, so really this correspondence between quaternion algebras and isogeny graphs of supersingular curves, is something that is essentially the foundational idea of the Charles-Goren-Lotter hash function, because what you can prove is that these action essentially forces the graph to be expander graphs. So to be essentially some very compact graphs where every vertices are separated by some very short walks, so that you can essentially get from anywhere to anywhere in a very short time, in a very short walk. So this is really fundamental to have some good quality hash function, of course, and even some cryptographic hash function in the end, which is really the interesting thing about this Charles-Goren-Lotter idea. This is not really what's used to define SIDH. If you watched Jesus' talk a couple of days ago on SIDH, you hadn't seen all this Dorian correspondence stuff. But it's something that's hidden behind SIDH and is something that in the essence governs the security of SIDH. So you need to understand the Dorian correspondence if you really want to look at the security of SIDH. And this is something that has been done by many people. Here I just cite in the footnote one paper, which is very recent, but really this all goes back to the initial work of Christophe Petit, Galbraith, and many other people who really looked at how you can use this Dorian correspondence to try and break the CGL hash function, try and break SIDH, etc. This also gives an equivalence between the isogeny path problem, which I stated before, and the endomorphism ring problem, which is the problem of given an elliptic curve, compute its endomorphism ring. Sorry, given a supersenior curve, compute its endomorphism ring, which is exactly the problem I mentioned before was studied by Coel in his PhD, and which, as far as we know, is a problem that seems very hard and to which we only know exponential time algorithms. So this equivalence has been known for a while heuristically and was recently proved formally by Benjamin Wissolowski in a very nice paper which appeared on ePrint a couple of months ago. And interestingly, and this is going to close the loop with what I said before, this is also a tool to build new schemes. So this really closes the loop with what I told you before. Do you remember this cryptanalysis lead to new cryptography? Well, again, we have this phenomenon where the first thing you have is this Coel, Lotter, Petit-Tignol paper back in 2014, which was really the first paper which looked into the Dorian correspondence and tried to make it effective, tried to give algorithms to move between quaternions and supersenior curves. They managed to only do it in one direction, going from quaternions to elliptic curves, which in the end partly breaks the CGL hash function idea, but which still doesn't impact directly other schemes such as SIDH, and even the CGL hash function, you can modify it and you can still build very interesting cryptography on top of it. Things that are maybe even more interesting than just plain hash function. If you put more stuff on it, you get something very, very cool, as I'm going to mention in a few slides. And then a few years later, you get the first signature scheme based on the Dorian correspondence by Galbraith, Petit, and Silva, which was a precursor to this key sign signature scheme, which I just mentioned, and which is a very important milestone for isogeny-based cryptography, because we suddenly have something that is better than any other post-quantum signature scheme in terms of size. Not in terms of efficiency, unfortunately, but this is something that we need to work on in the future. And so the last interesting application I'm going to mention of isogeny-based cryptography is something called time delay cryptography, which is this idea where instead of looking at complexity theory, hardness from a complexity theory point of view, like what's the complexity of breaking some assumption, you look really at the time that it takes to solve some problem. Time in terms of milliseconds, seconds. And so this, of course, it's very difficult because time depends on what your architecture is, what kind of algorithm you use. You depend on the parallelism you can use. And so you want to restrict algorithms to algorithms which are very simple so that you can be fairly confident that you know what the best algorithm to run them is, and also that they are very hard to parallelize so that you know that it doesn't really count how many parallel resources you throw at the problem. You still will need some fixed amount of time at minimum to solve the problem. So one very simple example of this is repeated hash functions. So you just iterate a hash function. Of course, you know no better way, if you want to evaluate 10 times SHA, there is no better way than one after the other evaluate SHA. Of course, this is a good sequential function, but this is not very algebraic, so you cannot do smart stuff with it. Another thing you can imagine is repeated squaring in a group. This is very easy, very hard to parallelize if you don't know the order of the group. And so this is what's behind this time delay cryptography, which has become very popular in recent years. And chains of isogenies, so isogeny walks, are another potential candidate for this kind of sequential functions, which, because they have a lot of algebraic structure, can make something called verifiable delay functions, where you have this interesting property that evaluating the function takes some minimum amount of time. But if I give you the answer to the solution to the function, then it's very fast to verify that the solution is the right one. And then there's another primitive that's very recent that will be presented at Eurocrypt in 2 weeks, which is called delay encryption, and which is something that's really unique to isogenies. Like, we know no other instantiation of this primitive from any other kind of assumption, and which is something like identity-based encryption, but where you replace the idea of deriving the private key, the private key associated to an identity. You replace this with the idea of having a slow operation. So you can encrypt to an identity, but before this identity can decrypt, you will need to take a long time to derive the private decryption key. And so this is very interesting to make some protocols like auctions, for example. And this is something that potentially may find applications very soon in blockchain protocols. So one word of warning, nothing of this is post-quantum, because it's very much based on pairings. So if you can break pairings, then you can break these assumptions. But still, it's interesting because it's the only way we know to instantiate delay encryption. Verifiable delay function, you can even instantiate it from just generic things. If you want, you can even instantiate it from hash functions, although it's very expensive. But delay encryption is really unique, and really we only know how to do it from isogenies. So, of course, the main question that you will ask is, are isogenies for real? Are we going to see isogenies in production soon? So to answer this question, I'm going to just leave the word to my comrade, and I'm going to point you to his talk at Real World Cryptography back in January, which is on YouTube, of course, and where he will tell you that SIDH Psych is definitely ready for standardization. This is something that, of course, has some drawbacks. Of course, speed is a serious problem. Of course, it's maybe less trusted than lattice at this point because it's younger, so it has been less studied, but it's something that you can really use. And if you really care about compact keys and compact ciphertext, it's something that you must consider for your application. All the rest, well, of course, it's not in the needs post-quantum computation. It's even younger, it needs more research, but at least they hold some promise and they may find applications in the future. But for those, of course, we can't really say that they are ready to be put in production. This will require more work. And so now the question which I started my talk with, and which I'm going to open to your questions, essentially, it's what's next? What's going to happen in the next years? So let me make some bold predictions quickly, and then let's open the floor to questions. So the first big and important problem, in my opinion, is the cost of isogeny evaluations. As I told you, this is something that we can do efficiently, but maybe not as efficiently as one may hope. So an isogeny is, as I said, is just some rational fractions which represent the action of the isogeny on the points. And something very important is the degree of this isogeny. And so for a long time, we thought that there was no way to go around the degree. If you want to represent an isogeny, you need to write polynomials which have the same size as the degree of the isogeny. And so you have a kind of natural lower bound, which is big O of the degree of the isogeny. And then just 1 year ago, there was this surprising result, which proved that actually you can go below this bound and you can go to square root of the degree under some conditions, which are exactly the condition we encounter in isogeny-based cryptography. And so now the natural question is, can we do better? The only natural lower bound you can imagine is a big O of log of the degree, but we're very far from this, and I don't think you will find anyone who thinks this is realistic, that we can really reach this bound. But then the question is, what is the optimum? And now, if you want me to give a prediction, I think that this is a very hard question that maybe we won't have an answer in the next 10 years. But I would certainly be interested in seeing at least some progress toward proving lower bounds to this problem, and maybe doing even better. And now the question is, as long as we don't have algorithms that run in log of the degree of the isogenies, we're stuck to having to find elliptic curves which have some torsion points of small order. This is a very important condition for the algorithms to be efficient. And so this restricts the kind of primes you can use for isogeny-based cryptography. And so depending on which cryptosystem you are going to use, you will have constraints like SIDH takes primes such that p plus 1 or p minus 1, that's more or less the same, is equal to a product of two small primes. Then there's this new idea beside, which requires p squared minus 1 to be entirely smooth. And this is a much more harder condition to meet. And SkiSign also has something similar, where you don't want full smoothness for p squared minus 1, but you want more than what you have in SIDH. So these are things that are hard to find. Like this kind of primes really requires some very hard searches. And there's going to be a very interesting paper next Eurocrypt by Costello, Meyer, and Nyrig. Are you in, Patrick? I don't remember. Which gives new ideas to find this kind of primes. And now the natural question is, how far can we go? It seems very difficult and to get primes as good as the one we use in SIDH. And so maybe this means that B-side will never be competitive with SIDH. Maybe these primes don't even exist, to be honest, so that there is no hope in finding them. And the same story holds for SkiSign, but SkiSign doesn't have any competitors. So at least for SkiSign, it's a very important question to do the best efforts we can to find these primes, so that we can have the best SkiSign we can, and we can potentially standardize this kind of signature scheme. And so this is the next question: is SkiSign going to be standardized? And I'm going to leave this question open. You can guess my answer, and I'm just going to recall that NIST has promised to reopen the competition to new signature schemes soon. And so SkiSign looks like a natural candidate for this reopening. In terms of signature, the natural question is, if NIST is reopening for new schemes, does CFISH have a future? Now, this is more delicate because CFISH has a huge potential because it opens the way to threshold signatures, ring signatures, which are as efficient as the scheme itself. However, quantum security is unclear. It's very difficult to instantiate CFISH. Like, we have one instantiation, and it took months of computation to produce the parameters. And if we want to move to higher security levels, this is going to become impossible. So the real hard question is, can we make CFISH easier to instantiate? Can we go around this problem? And my guess is that we may see something in the next years, because probably we haven't explored all the possible parameter sets that are out there. And if we can do that, then CFISH definitely holds promise for the future. The next question is trusted setups, which is something that I didn't mention, but and it's actually a very nasty feature of these time delay protocols. They all need a trusted setup which generates a supersingular curve with unknown endomorphism ring. And now the funny thing is that we don't know how to do that. It's very important that we produce these elliptic curves. They are naturally produced by schemes, like when you do SIDH, naturally the public keys are elliptic curves with unknown endomorphism ring. But the problem is that at least one person knows the endomorphism ring, and that's the person who produced the curve. And we don't want that. We want elliptic curves, supersingular elliptic curve, where no one knows the endomorphism ring. And so this is, we don't know how to do it in general. We know how to do it with multi-party computations, so that if at least one participant in a group is honest, then no one will know the endomorphism ring, which it's kind of okay, but and we have easy protocols to do this, but it's kind of unsatisfactory in the way that ZK proofs, like in the kind of ZK proofs, zero knowledge proofs that we have to instantiate these schemes, and so it's a bit difficult. And so one question which I really like to see develop in the next years is, will someone please implement these schemes? So there was some interest recently, and we may see these, maybe not for the time delay stuff, but more just for SIDH. Because even for SIDH, it would be interesting to have a starting elliptic curve which has a known endomorphism ring. So I'm confident this is going to be a direction in the next years where people will think a lot about this. And really, this thing of zero knowledge proofs of isogeny knowledge, I think this is going to be a big thing, because it's already fundamental for isogenies. for signatures, for isogeny-based signatures, but it's also important for a lot of other problems which are not directly related for signatures, but which may have important applications. So, for example, there was a recent preprint by Dobson, Galbraith, myself, and Zurbernik, which looks at the SIDH proof of knowledge and gives some interesting results. And now, if we can solve these problems of trusted setups, then the next question is, are these things going to be adopted in blockchains? For example, Ethereum has been very active on verifiable delay functions. Will they like delay encryption, and will they want to use delay isogeny protocols for it? This is certainly a sexy application, and it's unique to isogeny. So it's a good challenge to try and implement this delay encryption. But with the challenge come a lot of, with this goal come a lot of very difficult challenges, not the least the fact that these protocols are extremely space and bandwidth hungry. If you want to implement something that has a delay of 1 hour, for example, you will need to store terabytes of data for evaluating the delay encryption. And this data needs to go very fast from storage to CPU. So it's very difficult to implement these kind of things. So this is a beautiful challenge, which I'm pretty confident some people will take, because come on, isn't it so funny to just store terabytes of data and move them from memory to CPU very fast? I think it is. So I really hope people will look into this. And so, of course, there's many other questions, but I think I will let you ask those questions now, because I've really been speaking for too long. So thanks for your attention, and please give me your questions.
Thank you very much, Luca, for the very nice presentation. I do have a few questions here for you, so let's see if we can have a nice discussion. First of all, to answer your question in the presentation, the paper for B-side is by Michael Mayer, Michael Nerick, and Craig Costello, not myself this time. So you show the graphs in your presentation for the complex multiplication that is related to C-side and C-fish, and also the supersingular isogeny graph for over FP square that corresponds to SIDH and psi, for example. And definitely you can see the structure, the symmetry there. Do you see any connection between that kind of a structure, the symmetry that you see in one, for example? Do you see any relationship with cryptanalysis, with the security of the schemes, or shouldn't be seen that way?
I mean, it's clear that the symmetry behind these graphs is very much related to Kuiperberg's algorithm. So something I didn't mention is that all these systems based on cryptographic group actions, and so in particular C-side, C-fish, etc., they are all vulnerable to a quantum algorithm which has sub-exponential complexity. So it's not as good as Shor's algorithm, but it's much better than the best classical attack we have. So it sits in between. And so this is a fascinating topic, and the algorithm, Kuiperberg's algorithm, is a beautiful algorithm, and really is based on the fact that there is a group action, and so you have this symmetry. Essentially, the group of symmetries of this graph is going to be the group itself. So that's how the symmetry comes in one way. It makes cryptanalysis much easier, at least quantumly. Classically, we don't really know how to exploit this for cryptanalysis directly. So that's of course a very important question. But at the same time, if we knew how to do better than the exponential algorithms we have, those algorithms would also apply to a discrete logarithm. So we would have better algorithms to break discrete logarithm, which is very unlikely. So I would say no, although there is one minor detail, is that in complex multiplication graphs, we do not care about the order of the set being a prime number. So in that specific case, you may have something which doesn't break discrete logarithm, but breaks classically those kind of instantiation of complex multiplication where the order is not prime. So yeah, there may be something, but we haven't found it yet.
All right, thank you very much. Okay, another question. Apparently the new fight, lattices versus isogenies. How do you see how the security history is moving forward? The cryptanalysis maturity. What's your opinion on that respect?
It's hard to tell, of course. It's hard to tell. one thing is sure, isogenies will never beat lattices in terms of speed. And I don't think lattices will ever beat isogenies in terms of size. Unless isogenies become less secure, and then you need to increase parameters, and then, yeah, of course, the size will become worse for isogenies. But this goes to your question, what's up with cryptanalysis? How much are we confident in the cryptanalysis for isogeny based crypto? So one big question is, what's the quantum security of schemes based on group actions? This is a very tough point, because evaluating the efficiency of Kuperberg's algorithm, it's not easy. So we have lots of paper last year, Zerocrypt, 2 years ago, which study the supposed efficiency of Kuperberg's algorithm, and you can see like a very diverging numbers. There's a whole range of kind of parameters which some people claim would reach NIST-1 level. So this is very complicated to say, and this has a huge impact on performance, because if you go to the higher end of the proposed parameters, then C-side becomes really slow, and parameters become as large as SIDH or even larger. So the interest of C-side as a pure key encryption, key exchange scheme becomes very doubtful. But still, you have all the other applications which could be interesting. So this is the first point. Then now, if we look at the other schemes like SIDH, SIDH has been studied for 10 years now, and it's a difficult problem to study because it is not based on the generic isogeny path problem. If you ask me, I think the isogeny path problem in general, it's safe. Like we are now having this wonderful reduction, which are even proven, which relate the isogeny path problem to the endomorphism path ring problem. So now this is a much older problem, which was studied already 20 years ago. Maybe by not so many people, but which genuinely looks difficult, because it really seems difficult to go from the world of supersenior curves to the world of Quaternion algebras. There's certainly a lot more work to do, but at this point, I'm starting to feel confident that the isogeny path problem is safe. Now, the SIDH problem is not the same thing as the isogeny path problem. So the dog will agree with me that more...
Apparently. He's complaining a little bit, though.
Yeah. He's telling me, do the research, do the cryptanalysis. So
yeah.
The best algorithms we have against SIDH are exactly the same algorithms that we have against the generic isogeny problem. And so this seems to be very well understood. I don't think we can do much better than what we already have. But then you have all these other field of torsion point attacks that exploit the extra structure, the extra information that is inside SIDH. And this is much more difficult to evaluate, because if some parts move, then all the rest moves. For the moment, these attacks do not impact SIDH, but then eventually they may lower the exponents in the security of SIDH. My feeling is that we're getting to the point where these attacks are reaching the limits of what they can do. Some others will disagree with me. I will think that there is still hope to improve these attacks to get to the point where they really have an impact on SIDH. This is something interesting that we're going to see develop in the next years. But I would say that in that respect, there is not much difference to lattices. There are still huge debates on what the security of lattices is, what the exponents of lattices is. There's lots of discussions on the NIST forum. And of course, we are pretty confident that the best attacks we have now against lattices are as best as they can be, and that we've been looking at these problems for a while. And so a new breakthrough is unlikely, but you will never know. And so maybe the exponent in solving SVP or solving CVP will change, and then you need to change parameters for lattices. This could happen as well for lattices as it could happen for SIDH. So I would say that at this point, we're playing level for SIDH and lattices.
Great. This is a fascinating topic, and we can probably talk about it for the whole day. But
and I cut on the security of all the other ones, like security of ski sign. Oh, that's much more complicated. So that's another fascinating topic which people should work on.
Absolutely. Unfortunately, I think we're close to the end of the hour of the time. But Luca, thank you very much for your time, for the great presentation. It was awesome. Also, thanks for the picture of the pirate there. That way, people won't believe I'm crazy when I gave the introduction at the beginning. He's a
put the
real
link again.
pirate. Yeah.
Go watch the movie.
Thank you. All right. So thank you, Luca. And now for the oh, maybe there is another question there. Francisco is making a question that I see now. Can you mention the main challenges for implementing ski sign in constant time? And maybe with that one, we close the presentation today.
I mean, Francisco would have asked the main challenge to implement ski sign point, and that's already a challenge in itself. I'm sure Francisco has looked into the code and he sees it's a mess. There's one first challenge. We have a huge dependency on PAR-EGP, which is a lovely computer algebra system, but you don't want to have that dependency in a crypto system. So that's the first challenge. Get rid of PAR-EGP. That means re-implement so many algorithms related to lattices, and really specialize them to the kind of four-dimensional lattices we use in SkiSign, which has nothing to do with the lattices used in lattice-based crypto. So, I mean, even before thinking of constant time implementation, there is really a huge challenge in implementing SkiSign in a self-contained way without dependencies, without external dependencies, and in optimizing this, because in the paper at Asiacrypt, we were a little bit like we just followed our intuition on what a good prime would be, what the best compromises would be, but there are so many knobs you can turn in SkiSign, so many different compromises you can make, and this is really a huge problem to really look into the different compromises and find really the best one for your application. So even before thinking about constant time implementation, I would think about all this stuff. Then once you have this stuff, the isogeny evaluation part is essentially the same as you have in B-sides, SIDH, etc. So that's easy. And really the challenge is then implement all these Quaternion algorithms in constant time, which, it's again going to be a real challenge. But I mean, we know how to do it. It's going to be a lot of work, but we can do it. Suppose the first thing is to try to make the code much less big, much less verbose, so that you can really focus on some really small steps, which you can then little by little make constant time. So we're of course working on it, and we will soon have something new, I think, on this stuff. And then we will certainly be looking for more people to join the efforts and work together on having the best implementation of SkiSign out there. We're definitely looking to break the second to sign barrier soon and possibly get to the hundreds of milliseconds. That would be great.
Excellent. That sounds exciting. And as I promised to the audience, this could take the whole day discussing about these kind of things. So thank you very much, Luca, for your time, and I'll stop abusing your time. And for the audience, we'll take a break now and continue in about half an hour at 11:30. There's an announcement from the general chair. We are going to have a public call now during the break, so you can go to the main platform of the Latin Crypt website, and there is a networking button on the bottom left, and you can enter there and enter the call. We're going to be there to have a chat, and so thank you very much again, Luca. See you around, and see you in about 30 minutes for the rest of the conference.
Thanks very much for the invitation. It's always a pleasure. Hope to see you soon in person.
Yeah, me too. See you.
Hello, everyone.